In this lecture, we will have a quick introduction to negative feedback. We will take up the more advanced aspects of negative feedback in a different lecture. So this is meant to be a refresher because in this advanced course you are already assumed to have encountered negative feedback in an earlier course, in a prerequisite course, but we will quickly review it in a very short lecture. So what does a negative feedback system consist of? It consists of broadly, operationally it consists of three major portions. You have a desired quantity, you have the actual quantity, and you want to drive the desired quantity toward the, you want to drive the actual quantity towards the desired quantity, or maybe a replica of that. In the case of electrical engineering, we are trying to build amplifiers. So we will assume that you are trying to build a negative feedback amplifier where VO is some K times VI, and of course because it's an amplifier, K is greater than 1. How do we do this using negative feedback? As you all probably know, you take a small portion of the output quantity. In this case, I am representing the output quantities by voltage quantities. So you take a small replica of VO, and we will call that some F times VO. We compare that with VI by performing a subtraction operation. So if you subtract F times VO from VI, you will get what is called an error quantity. We will represent that as VE. Now the magnitude and sign of VE will tell you how far away VO is from VI. And then you magnify this error quantity using a forward amplifier whose gain we will term as being equal to A. So now the quantities describing the system are VE equals VI minus F times VO and VO equals A times VE. And now we can now manipulate these two to get the actual relationship between VO and VI, and VO is nothing but A times VI minus FVO, and VO is AVI minus AFVO, and therefore this expression holds true. And finally we can write VO by VI as being equal to A by 1 plus AF. Now this is the common way of writing this, but now I will write it in a slightly different manner. I am going to write it as 1 over F times AF by 1 plus AF. Now the reason I am going to write it in this form is twofold. Number one, we know that the ideal value is in reality VO should be some replica of VI. Now when does that happen? That happens when you have AF being as large as possible. Let us just write that down separately. So so if AF tended to infinity, then VO by VI will become equal to 1 over F, which is the same as K. So now you have achieved your amplifier that you have been wanting to design. So clearly F should be less than 1 since K is greater than 1. Now this quantity AF is called the loop gain of the system, and very often it is the most important quantity associated with the negative feedback system. Why do I say it is the most important quantity? So in reality, even though you might have studied, earlier that you want A to be as large as possible, which is true, it also, you will find that the actual quantity that matters for most of your feedback systems is A times F, because it is primarily only when you have A times F that is much larger than 1 that the quantity that I have circled here goes to 1. Now this is definitely looks good. Now what happens if you have systems that are frequency dependent? So we will club all of these together and assume that it is only the forward block that is frequency dependent. Now, so what we mean is the forward block is no longer A, but it is some A of S in the Laplace domain. If that happens, then VO by VI of S is what we are trying to derive, and that is clearly 1 over F times A of S by 1 plus F times A of S. And now you can see that if A of S starts reducing with frequency, then you can see that is frequency dependent. For example, it starts reducing with frequency. You can see that loop gain will start reducing with frequency, and as we know, negative feedback is operating only when the loop gain is extremely large. So at frequencies where F times A of S is much larger than 1, VO by VI of S becomes very close to 1 over F. If A of S starts degrading with frequency, that you will reach a point where the loop gain becomes comparable to 1 and negative feedback is said to be no longer operational. Now we are specifically going to look at the denominator of this expression. F times A of S by 1 plus F times A of S. So if you look at this, the denominator expression, there will be frequencies where it is possible for 1 plus F times A of S to become equal to 0, because now A of S is a function of frequency. It has both magnitude and phase. Therefore, it is possible for 1 plus F times A of S to become 0. What implication does this have for the system? So if you go back and look at the expression for VO by VI of S, you can clearly see that if the denominator goes to 0, then VO by VI goes to infinity or is indeterminate really. What it really means is VO is no longer a function of VI, or to put it in different terms, you can have an output VO of S even if VI of S were equal to 0. So what this means, it is possible to have finite VO of S even if Vi of S were equal to 0. In other words, your system is unstable. So normally a stable system is a bounded system. You will get an output only if you apply an input. So this means that there is a possibility of instability. Now you would have seen this in many forms in your undergraduate courses or in your in prerequisite courses in either analog circuits or control engineering or linear IC design. A basic idea is that this can be put in many different forms, but in this particular course we will see instability in this very specific form because we are dealing with systems which have a certain number of poles and zeros. So we will express it in this manner. So we will say that we will write it in this form: 1 plus f times a of s is 0. We will rewrite it as f times a of s, or I'll just write it as loop gain of s, is equal to -1, and this has two portions, as you might imagine. The magnitude of the loop gain should be exactly equal to 1, and the phase of the loop gain should be -180 degrees. If these two conditions are satisfied, there is potential for instability in the system. So these are the two criteria that we are going to apply. We will go one step forward and say that it is possible for the system to be unstable even if the loop gain were greater than 1. You will learn the reason for this. You would have learned the reason for this in your control engineering course. So we will not cover that in this course, but I just want to point out that this is the condition that we will be applying for instability.